Okay, very good. Well, let's now go on and talk about strain, and then we'll combine the ideas of stress and strain to talk about strength of materials. All right? Hang on one sec. Okay, we've defined stress. It has units of a pressure, but whereas pressure is always a compressive stress, stress allows us to talk about a wider variety of things. Tensile stress, where we're pulling something apart, or shear stress, where we're trying to bend the material, or anyway, the force is now parallel to the surfaces. Let's go on then to talk about strain. So materials will deform when we apply a stress, and strain describes how much they deform. Let's imagine I have a piece of material here. I'm going to try and draw this. It's supposed to be a little bar. Okay, now suppose we apply a tensile stress to this. Then we might expect the material to deform. It might become a little bit longer, like so. Didn't draw that very well, but I hope you get the idea. And the amount of deformation is described by the strain. If the original length of our piece of material was L0, and if the new extension is delta L, the amount it's stretched out by, then the strain is just defined as delta L divided by L0. Okay? Very good. So that's the strain. Hey, do you remember the units of stress were pascals? They were pressure units. What are the units of strain? Well, strain is a length divided by a length. It has no units. It's unitless. It's just a pure number. Okay? Now, when we apply a force to a material and it exhibits strain, we can talk about three different regimes. Oops. So now we'll be combining the ideas of stress and strain. The first regime is low stress, or really low strain. In the low stress regime, the material will be elastic. That means that it will exhibit some deformation, but the deformation is reversible. And importantly, the deformation will be proportional to the stress. That is, we can say that the stress and strain are related. The stress is just equal to a constant times the strain, okay? This is supposed to be reminiscent here of Hooke's law for a spring, where the force is equal to a constant times the amount that the spring stretches, F equals Kx. Here, the constant has a name. It's called the modulus. And actually, there are different types of modulus for different types of stress. So there's compressive modulus, or what's called a bulk modulus. There's as well as shear modulus and so on. So in the low stress regime, the material is elastic. Then there's a high stress regime. Where the material deforms, but the deformation is irreversible, and this is called plastic deformation. And then finally, if we apply a very high stress or a sufficiently high stress, the material might just break. And this is called failure. Okay? Here, let me illustrate these for a second. Here's an object, this spoon, and I can apply a shear stress on it by trying to bend it. If I apply a small stress, it springs right back. That's an elastic strain, okay? If I apply a large enough stress, it exhibits plastic deformation. It doesn't bend back, okay? This is made of metal, which is very ductile. That means it will deform plastically a lot, okay? Here's another object. This is made of a plastic. I think it's a compostable fork or something like that. Again, I can apply a small strain and a small stress, and the strain is elastic. It recovers when I remove it. And the amount of strain is proportional to the stress, elastic, okay? If I apply a large enough stress, I'll get plastic deformation and then ultimately failure. This fork was brittle, which means that it doesn't stay in the plastic deformation range very long before it fails. Okay, here we can describe what we've just seen and what we've just been talking about with a curve called the stress-strain curve. Hang on for a second. Very good. Okay, a stress-strain curve is just a graph of stress versus strain for a particular material. Excuse me. Yes, I want to undo. There we are. So, and typically strain is denoted on the x-axis. Often it's given in percent. And stress is denoted on the y-axis. And our typical material will exhibit a stress-strain curve that looks like this. It starts out linear, that's the elastic regime. And then at some point, the curve will begin to bend over. This is the regime of plastic deformation. Try that again. And finally, it'll exhibit failure. And we just have to stop drawing the curve at that point because the material doesn't exist anymore and the stress is released. So notice there are different ranges of importance here. There's the elastic range. There's the range of plastic deformation. And finally, there's the point of failure. Okay? The transition points are important. The stress at which the material starts to exhibit plastic deformation, that's called the yield stress. Or the yield strength. And the point at which it fails is called the ultimate strength. Okay, so there's a stress-strain curve, and which describes these different things we talked about: elastic deformation, plastic deformation, and failure. Okay, now let's use what we've just learned to do an example. Let's see if we can figure out the ultimate strength of Jell-O, and then let's find out a relative strength. Let's find out how large a Jell-O cube I can build before it collapses under its own weight. All right? Sounds exciting. So first, what's the ultimate strength of Jell-O? Well, to do this, we have to see if someone's done an experiment and if we can just look up their answer. And in fact, someone has. So hold on for a second and we'll take a look at that. Oops. Okay, here it is. paper describing the tensile strength of gelatin jellies. And we'll take that to describe Jello, which itself is a gelatin jelly, I guess. Okay? And here's the data. Stress as a function of strain, and you can see the failure point here. Okay? And the failure point is about 100 and, let's just take it to be 140 of these units. Unfortunately, the units here are grams per centimeter squared. So he gave a pressure, but he didn't give it a pressure in newtons. He gave it in grams per centimeter squared. Luckily, we can convert that. 1 gram per centimeter squared is 100 newtons per meter squared. And so, thinking about that myself here. Excuse me. I'm not quite sure that's right. Let me just stop for a second. Nope, it was wrong. Here, let's correct it. So the ultimate strength of Jello, we said, is about 140 grams per square centimeter. But 1 gram per centimeter squared is the same as the following. We have to convert from grams to kilograms, 10 to the minus 3 kilograms per gram. And we have to convert from centimeters squared to square meters. So there's 100 centimeters per meter, and so there's 10,000 or 10 to the 4th centimeters squared per meter squared, 100 times 100. So we have on the denominator 10 to the minus 4 meters squared per centimeter squared. And then we can easily work out that 1 gram per centimeter squared is 10 kilograms per meter squared, or 10 pascals. So sigma u is about 1,400 pascals. Okay, and now let's figure out something really important. Let's figure out the size, the maximum size of a self-supporting Jello cube. Largest possible self-supporting Jello cube. Okay, can we do it? Here's the idea. Imagine we make a Jello cube and set it on a surface. We'll imagine the cube has dimensions d by d by d. The largest self-supporting cube will have a mass such that the compressive stress at the bottom of the cube will equal the ultimate stress. When that's true, then that's the largest possible, because any cube that was larger would exceed the ultimate stress at the bottom of the cube, and so it would start to fail, and the cube would collapse. Okay? So let's see if we can, so that's the idea. Let's see if we can figure this out. So the force exerted by the cube on the surface is just m times g, and then we can use that to figure out the stress. But first, let's find the force. The force, of course, is just the mass times acceleration of gravity, and the mass is just the density times the volume. The volume here is d cubed. Okay? On the other hand, the area of the bottom of the cube is just d squared. And so the compressive stress exerted by the cube It's just the force over the area. It's rho d cubed g divided by d squared. And so it's just rho d g. Okay? For the largest cube, then we know that rho dg, the compressive stress, should equal the ultimate stress. And so D should be ultimate stress divided by rho times G. Okay? Not so bad, right? Finally, let's put in numbers and find the size of the largest possible self-supporting Jello cube. So D then is going to be the ultimate stress, which we said was about 1,400 pascals. Now we have to divide that by the density of water, which is 1,000 kilograms per meter cubed, and also by G, 9.8 meters per second squared. Okay, turning the crank, we have 1,400 divided by 1,000, that's 1.4, and then we have to divide that by 9.8. So it's about 1.4 divided by 10. 0.14, or exactly, it's 0.143 meters. Okay, so 143 centimeters on a side. Okay, well, there it is. Now you can go home, buy some Jello, and see if we're right. But we've just predicted the largest possible self-supporting Jello cube. All right, very good. Hey, one more thing before we stop this section. The stress law for our Jello cube. Sigma equals rho g times d. This is an example of a scaling law. It tells us how the stress varies with this object's size. Okay, the stress due to its own weight varies with the object size. And notice, what we found is that the stress is just proportional to the size. Okay? For example, we can use this to solve problems. This is kind of interesting. Suppose my Jello cube was not 140 centimeters, but it was 100 nanometers. How many times its weight could it support then? If it's 140 centimeters, it can support 1 times its weight. Any more weight and it will collapse. So, for example, let's make it 140 nanometers, just to make things easy. Then the stress is much, much less than the ultimate stress. Because sigma u is rho times g times the value of d that we just found, 143 centimeters, which I'll write as d max. Okay? So that means that the stress could just be written as the ultimate stress I'm sorry. Excuse me, while I just fix what I've done here. What I meant to say is this, that the number of cubes that we could support, in other words, the number of times its own weight that it could support, that's given by the ultimate stress divided by the stress actually exhibited on the object. And because the stress is proportional to the size, that's just equal to D max divided by the actual size of our cube. And in the example that we're doing, the maximum size is 0.14 meters. But the size we're considering is 140 nanometers, or 1.4 times 10 to the minus 8 meters. And this works out to be 1 times 10 to the 7th. Okay? And this is the example that I wanted to get to. I mean, this is the result I wanted to get to. The stress on the object is given by a scaling law. And we can use that scaling law to find out something interesting. Whereas a 140 centimeter wide cube can only support its own weight and nothing more, a cube that was 10 to the 8 times smaller could support 10 million times. I'm sorry, a cube that's 10 to the 7 times smaller could support 10 to the 7 times its weight. It could support 10 million cubes. So in that sense, this scaling law is telling us that small is strong. The small cube could support millions of times its own weight, whereas the large cube can barely support its own weight. Okay? All right, let's stop here.